Alright, this lecture is going to be me talking you through adiabatic heating and cooling. Remember, adiabatics involves changing temperature, but not changing the heat that's in the parcel of air. So we'll talk about water that evaporates, adds moisture to air, it begins to ascend or rise above an orographic boundary, and it condenses out all the moisture, and then eventually it descends, the dry air, very dry air that's warming due to compression, and we create this rain shadow. So when I talk about this, conceptually, here's what's going on. We get evaporation of warm, moist, well, let's just say warm water evaporates. It rises, it cools adiabatically. It drops all the moisture out early on this side. This is where we get our rainforests and other green, lush vegetation. It continues cooling. It's very, very dry. As it falls, it compresses. Here it's expanding. It's cooling due to the expansion. Here it's warming due to compression. So any moisture that's available over here, the air that's warm and dry evaporates it, picks it up, and it generates these warm, dry winds. And these are what create these desert conditions. So when we solve this, here's a general picture that you'll be looking at. Always pay attention to the initial starting conditions. Here's a 25 degrees Celsius starting temperature and a relative humidity of 50%. And I'll look at these arrows here in a minute, but they're telling me that the air is going to be rising. It's going to it's going to reach its dew point. It's going to condense out all that moisture, and then it's going to reach the summit before it then subsides or falls back towards Earth, descends back towards, the far side, the leeward side, and this is going to be warm, dry air. When solving these, make sure you're paying attention to what the question is asking for. I recommend you refer to 8-2 several times. When interpolating numbers or data to get more accurate values, use your graph. So here's the first one. Number 1, land features affect local climate. So when I look at this, 25 degrees and 50% starting conditions. So what are the 3 phases in the purple arrows? Well, here I have warm air, warm moist air that's going to be rising. It's going to be cooling at the dry adiabatic lapse rate. It's going to be cooling at 10 degrees C per 1,000 meters. Once it reaches dew point, it's going to continue cooling, but it's going to cool now at 5 degrees C per 1,000 meters. And then on the far side, on the leeward side, so notice the windward side, it's all cooling. On the leeward side, it's going to be all warming at the dry adiabatic lapse rate. So I'm going to do a practice problem with you, and this is the general sequence of questions I'm going to ask you. So 1 through 11. So I'm just going to jump right into the numbers. So what is the air's capacity at sea level? Well, we're going to be using 8-2 repeatedly. At 25 degrees, the air can hold 20 grams of water vapor. What is the water vapor content at sea level? Well, it's a 50% relative humidity, so it's holding half of 20 grams. So it's holding 10 grams of water vapor. What is the dew point temperature? Well, find where the capacity of 10 grams is, and that's 15 degrees C. So what elevation will the air at sea level reach its dew point? Well, okay, it's going to cool at the dry adiabatic lapse rate. So air rises and cools at 10 degrees per 1,000 meters. Air will reach its dew point after it has ascended or risen 1,000 meters. So when will we start finding clouds? Well, we're going to find them at this 1,000 meter elevation or altitude. This is where the air has reached saturation. It's reached its capacity, and it's at its dew point temperature. This is what we will call the cloud line. So what will be the temperature of the rising air at the summit of the mountain? Well, the summit is 5,000 meters or 5 kilometers. So the air must cool at the wet adiabatic lapse rate, which is 5 degrees C per 1,000 meters. So it's going to cool another 20 degrees. So it went from 15 degrees C, it lost another 20, and it's going to end at the summit at -5 degrees C. So how much water vapor will be condensed out of the rising air at the summit? Well, at -5, you'll find an 8-2, it can only hold 2.5 grams of water vapor. But we started with 10 grams, right? We started with 10 grams up here. So the air must have precipitated out 7.5 grams of water vapor. It lost this of the original water vapor that's now in the form of precipitation. So what's going to happen to the temperature of the descending air? It's going to warm up. It's going to warm up at the dry adiabatic lapse rate. It's going to warm up at 10 degrees C per 1,000 meters. As it falls, it's going to heat due to compressing of the air molecules, right? Adiabatics. You're changing the volume in which that heat is distributed. So what will be the air's temperature when it reaches the 2,000 meter plateau on the leeward side? So air is going to descend and heat at 10 degrees per 1,000 meters. It's going to fall 3,000 meters. So it's going to heat up 30 degrees C. It's going to go from -5 degrees C to reach at 25 degrees on the plateau side or on the leeward side. 25 degrees. I've simply added 30 degrees C to -5. So what's going to be the relative humidity on the leeward side at 2000? Well, the air has 2.5 grams of water vapor. Remember, it lost 7.5 grams. Negative 5 degrees can only hold 2.5 grams of water vapor. So it has 2.5 grams in it. Its capacity at 25 degrees C, we said earlier, was 20 grams. So 2.5 over divided by 20 grams, right? Capacity at 25 degrees C is a relative humidity of about 13%. Very, very low humidity, relative humidity. So why do we find lush green side of a mountain? Why do we find a dry desert side? Well, the lush green side is a result of the moisture available on the windward side of the mountain. And the leeward side is a desert. This reflects the warmer, drier conditions of the air.